Hello learners, welcome to session 5 of unit 5 in the course Introduction to Abstract Algebra. In the previous section, we look at polar coordinate representation of complex numbers. So in this session, we are going to look at complex exponentials. You will learn how to represent complex numbers in exponential form. I am Mukaila Dasmani, your course instructor. By the end of this session, you should be able to express every complex number z in the exponential form. So let's look at the simple exponentials. The polar coordinate or the polar representation of complex number can be simplified by using the Euler's formula. So this is the Euler's formula. Let me underline that. We are going to make use of this Euler's formula. Exponent theta I equals to cos theta plus I sine theta. Okay, plus I sine theta. So that is a polar representation of complex numbers, and that's we are using the Euler's formula to do that. So where theta is a real number and e exponent z is a familiar exponential function defined by Taylor series. So by using the Taylor series, we can find the exponential of e as this expression. The power series representation for here we are looking at from simple important power exponential functions. So the power series representation for the exponential function e raised to the power x is given by this, and also e raised to the power z is also given by this. In particular, once you deduce that, you can find e raised to the power theta. So wherever you have x or z, you put inside your I theta. So it was 1 plus z, so plus z, then z square, you put I there, I theta there, in that order. So you simplify further, you get this expansion. So you can see that the power series of cos, sine, and sine of theta are given by this expression. So the cos theta is given by this, and the sine theta is given by this. And you can see that the sine are, look at the powers. So the sine theta are even given as the odd powers, and then cosine is given as even powers. 2, 4, 6. Fine, because here we don't have power. Talking about the powers. 2, 4, 6 in that order. So think about the two. Which of them is the even function and which of them is the odd function? So power series for e raised to the power q I theta equals to the power series for cos theta multiplied by I power series for sine theta. So once you do that one, you're able to find the, and using the Euler's approach, we're able to find the e raised to the power I theta as this expression. I theta as this expression. So you get cos theta plus I sine theta. So you can do further calculations, just do further proofs, further works. At the end of the day, you get the same result. So just use this expression here, e to the power I theta equal power series for cos theta, then dots, then you bring the I power series for sine theta, and then you get this results. Very beautiful results. That's the Euler's formula. E raised to the power iq equals to cos theta plus I sine theta. Very, very interesting. That's the beauty of mathematics. So we are looking at examples. We want to evaluate these expressions. So let me try to do some with you. So by using the Euler's approach or the Euler's formula, you are going to use that one, and don't forget the Euler's formula says that e to the power I theta equals to cos theta plus I sine theta. Okay, so we can do maybe one or two of these. So a is power pi on 2I will be equals to, so what do you see? You can see that I can get cos theta, and that is pi on 2 plus I sine theta, and now it's pi on 2. So pi on 2 from your calculator, this one you can even know pi on 2, 180 divided by 2, you get 90. That's why this equals 90 is actually 0. So you get 0 plus I sine pi on 2, and then sine 90 is actually 1. So in all, you get I. Okay. So let me do maybe last one with you. You can do the rest. Let's do the D. The D says that e to the power minus 1 plus pi on 2I. So let's use the Euler's formula approach. So here you can write this one as e to the power minus 1 multiplied by e to the power pi on 2I. So that when I use the laws of indices, I get e to the power negative I plus e to the power that's negative I plus pi on 2I. So by using the law of indices, so in that instance, I can write this as this equals to e to the power negative 1 brackets open, then I do the 1 in the middle. So you get e to the power negative I, you multiply by Euler's approximation of e to the power pi on 2I. And what do I get? Cos pi on 2 plus I sine pi on 2. So you simplify this further, what do you get? You get I. So you use the power negative 1 times I. And what do I get? You get I divided by E. Alright, so that's the answer for that. So simple. Now let's look at this also. Suppose that z equals to a plus bi is a complex number. Then z can be written in the exponential form as z equals to r e raised to the power I theta. And I think you agree with me. So here your r is given by this usual thing we know, and then theta is the arctan of b on a, which we have already also done. And don't forget about your quadrant in which it lies, the quadrant. Let's see example 10. Find or express the complex number z equals to 8 plus 6i in or as exponential form. So what do I do? We say that we can represent z as z equals to r e to the power I theta. That's what we said. So in that instance, let's find our r. Our r is the same as what? Don't forget about your magnitude of z. We've already done that one. A square plus 6 square. And what do I get? You get 10. Okay. So getting 10, then you find our theta. Theta because for the arctan, or you can say tan inverse. Arctan of that is b on a, 6 on 8. And what do I get? So you are leaving the answer in radians. So let's say 0.6435 in radian. Okay, let me clean this. 35 in radian. So you're leaving the answer in radians. So in radians. Okay, so having gotten your theta, but don't forget, you can see because it is both a and b are all positive, lies in the first quadrant. Therefore, that's actually our answer. Therefore, our z equals to, we are writing it in exponential form, 10 e raised to the power I can write 0.6435. Okay, you can also actually convert to answer 2 degrees. Don't forget about that. Okay, the next example, this is so simple, so I'll just give you maybe the answers. Your r will be equals to the magnitude of z, and that will give you 4 root 2. And then you can also find your theta. Don't forget about your quadrant because it's negative 4 and 4, the quadrant in which it lies. So you get if I'm doing straight away, pi minus arctan of, I hope you remember 4 on 4 is 1, and that gives me theta will be equals to 3 on 4 pi. Okay, therefore I can have my z equals to 4 root 2 e exponent 3 on 4 pi I. So that is very simple, very simple. You can do more, find more in your course material. There are a lot of examples there you can also practice. So try this one. Express the complex number this and this. That is, you have to z equals 17 minus 104i is 10i. 17 minus 10i, not 104i, 10i, and z equals minus 1 on 2 minus root 5i in exponential form.